Welcome to this lecture number 3 of module 2, and in this lecture I will discuss about the selection of converter configuration. In the last lecture we saw that various requirement, and those requirements here you can say we require high pulse number for having the better configuration of rectifier circuit or converter circuit. We should have the peak inverse voltage over this VDO, that is the DC output voltage without any delay, should be as low as possible, and we should have the DC output voltage, that is the ratio of E, that is the impressed voltage, should be as high as possible, and the transformer utilization factor should be near to unity. So, first requirement already I discussed in the previous lecture, that we should go for the high pulse number to reduce the number of harmonics, so that we can reduce the requirement of the our filter circuit, and but it cannot be very high due to the limitations of the converter cost and etc. So, we can normally go for the 6 pulse and the 12 pulse converters configuration. Second is that the peak inverse voltage, it is also related to the cost of the valve. If this value, the peak inverse voltage is very high, then we have to go for the very expensive valves, and therefore, we have to go for the as low as possible. To make it general, if Q, as you know, this is a number of valves in a commutating group. If it is even, then the peak inverse voltage will be the twice of the peak value of the impressed voltage, that is a EM. If your voltage of secondary side is EM sin omega t or sin omega cos omega t, then it will be twice of its peak value, and this normally occurs here when the valve with the phase displacement of 180 degree is conducting, then it will be 2 EM. But on other hand, if it is a Q is odd, the peak inverse voltage occurs when the valve with the phase displacement of pi plus minus pi upon Q is conducting, and will be equal to, that is already explained, this 2 EM cos pi by 2 Q. So, this value, if the VDO already we have derived, what will be the VDO in terms of series and the number of series valves as well as the number of commutating valves in a group. So, peak inverse voltage divided by VDO for the your even number, this will be your this, and for your odd numbers, this is your, when this Q is even, we are going to have this value, and once your Q is odd, we can get the pi upon SQ sin pi upon 2 Q. We will see this value for the different value of S, Q and R, and for given a pulse number, we will see in the next slide. Another requirement, as also I discussed, that we require this the DC output voltage, that is the VDO, when O means there is no delay, divided by E. E is the RMS value of the secondary side voltage, will be again given by this value. So, your VDO upon E is under root 2 QS divided by pi sin pi upon Q. Now, another important criteria to have a converter circuit that we should use, the transformer utilization factor should be as much as possible, means it should be properly utilized. So, here the transformer utilization factor, basically it is defined as the ratio of the transformer rating, here the valve side, we are talking about the secondary side, to the DC power output, and this should be as low as possible. Means the transformer utilization factor shows that if you reverse it 1 over TUF gives your efficiency of the transformer. So, this is again, it is in a mathematical term, it is defined as your nothing but it is your TUF, it is your PT divided by your VD into IDT. The PT is nothing but your the secondary side, here your RMS AC RMS divided by your DC power. To calculate what will be the PT, this is very clear. In any output of the converter circuit, it is the VD, that is the output DC voltage, and ID is the DC current, and we have assumed this DC current is a constant in your DC link. Now, IT, basically we can generalize this IT, this PT is nothing but your VT IT, means here we are talking the VA rating. So, this is the voltage, RMS voltage multiplied by the current RMS value, again it is the valve side that is flowing in the valve. To make it general, this IT we can write, it will be this value, that is depending upon your Q. Q is again your number of valves in a commutating group. to see this impact, how I have generalized this, here you can see if it is a three-phase rectifier one way, we are getting this is your in the this 120 degree, this is a conduction period, and for remaining period here 120 and 120, here it is off for one valve. Similarly, you can find this is valve 1, here you will get valve 2 and valve 3. Means it is conducting for 120 degree, and this value is your DC ID. So, we can get the RMS value if take this is the axis, and if you want to calculate what will be the RMS value of the valve side of the secondary, here you know this is your 1 over, we have to go for the twice pi, this is IT square, and here we are integrating 0 to this value is 2 pi by 3, remaining will be 0. Your ID here d omega t, this will be a square, this is square, this will be square. So, RMS value here just we have to take under root. So, if you are going to put this value and you are going to solve it, how much you are going to get it here? It is your ID square by 3. Because this 2 pi here will be 2 pi by 3, this should be cancelled, we are going to get this, means we are getting your IT, it is your ID over under root 3. And this 3 is nothing but the 3 valves in a commutating group. Similarly, you can see for other cases as well. So, we will get this expression in general. That is true for all type of configurations. We can write this RMS value of the valve side, it will be equal to your the DC current. Again, this DC current is assumed, it is a constant which is flowing in the DC link, divided by under root of the Q. Q again it is a number of commutating valves in a commutation group. Now, if the valves are in parallel, here if you see this configuration is nothing but we are having the windings here, this is your 3 windings, and we assume that we are having here valves 1, here we are having another valve, here we are having another valve, and the neutral is as a return path, if you remember. So, this is valve 1, 2 already we have written here. So, in this case it is the valve is only one in the series here. There is a possibility you can have the 2 valves in the parallel. Then that value here, this will be appearing here with R. R is the number of parallel valves that is here connected with the winding here. So, this is IT is your general term, this expression that we have to use here. Now, another term here is your voltage, means here is the PT here, it will be your is defined as EM by under root 2, this is RMS voltage of the secondary side. This is secondary side, already all the equations we wrote in the secondary side we are never write here for this case, because here whatever I am writing it is Im sin omega t, it is your instantaneous voltage of phase. So, this will be here under root 2, this is the RMS value into your this current which is flowing for that pulse, and if the number of pulses are p, it will be multiplied by p here. So, here number of pulses are 3, so it will be 3. You can also visualize here it is a 3 phase. So, you can say 1 phase multiplied by 3, but it is not always, you cannot say it is a phase wise, because the some of the transformer having the auto transformer or they are having the center tap transformers. So, it is the phase are single, but they are tapped together. So, it depends upon the pulses, that is more convenient rather than using the here 3 phase or 6 phase like. So, the P basically I am writing is the pulse number, and here this is your AC side RMS value of voltage, the current, and then we have to write the transformer utilization factor. That is why here you see I have written this PT is equal to P into EM over under root 2 and multiplied by IT, and that will be equal to your P here. That can be simplified because we can put this IT value in this expression, we will get this value here. Now, again the transformer utilization factor, if we are going to calculate this value, just put this value of ID and VD here. this Vd which I wrote here, this is basically we are talking there is no delay, and that is the VDO into ID here. Just put this value and just if you simplify, because the VDO already we have expressed in terms of your the Qs and this sin pi by Q. Just simplify this expression, you are going to get the transformer utilization factor, which is your pi over under root 2 under root Q sin pi upon Q. Here as I said, the reciprocal of the transformer utilization factor, it is nothing but it is just like a transformer utilization efficiency. Mind it is not a transformer efficiency, it is a transformer utilization efficiency we are talking. Both are totally different. Transformer efficiency, normally we go for the input over the output and the losses etc. is considered. Here we are not talking about the losses, we are even assuming the transformer is lossless. It is a utilization, means any material that is going to utilization, that information it is giving. So, one observation we can see from this expression, that the transformer utilization factor is only dependent on Q, even though R is also disappeared because R was appearing, but here this R is also vanished. So, to get this the transformer utilization factor optimal value, we can just differentiate it and then equate it equal to 0, and we can get what will be the optimal value for the transformer utilization factor, so that we can just differentiate here this factor, and you will find this Q will be the 3. Means in that factor, if you are going to take the what will be the QE of optimal value, you will find the Q is equal to 3 will come. Simply just differentiate that with respect to Q and equate it equal to 0, solve it, you will find the Q should be 3. So, now here the Q is 3, that is the optimal value, and now you can also see this whether is the 3 is correct or not, you can see from this table for the 6 pulse. This table shows that for a given 6 pulse, the possible combinations are the 5 combinations we can have, means always the multiplication of these 3 quantities, it is your 6 value. So, for the Q can be 2, Q can be 3 and Q can be 6 as well. So, here for this you can have the 2 Qs here, Q is equal to 2, Q is equal to 2, and then corresponding R and S value will be 1 and 3, R3 is 1. So, we have the 5 here the possible combination for it is this value is P is equal to 6. Now, if you put this values for all the Q, R and S, you will find this table where we are just going for. Now, you can see as our requirement, this peak inverse voltage divided by VDO should be as minimum as possible. Now, we have the 2 cases here, this and this is minimum, and both are same, means this value and this value, others are very high. So, we are having 2 values, means your serial number 1 and serial number 3 is giving minimum peak inverse voltage over your VDO. Now, your VDO upon E is the maximum for this, and of course, second option is your this, but the maximum we are getting for the serial number 1. Now, the transformer utilization factor, if you will see, as I said, it should be as near to unity. So, option here is only your this is less compared to other 2. So, now again with this combination it shows the optimal configuration can be either 3 or 1, because the 3 also here this is the second position this value, but this is the better in the 3 configuration at the when you are going for Q is equal to 3, 1 and 2 here we are having this is better and this is better. For 1 configuration we are having this better and this better. Now, choice either it will be 1 or 3, but it will be preferred that we can use 3. The reason is because we are having 3 phases and very easily we can identify the number of valves in a group, because we are having 3 phases. Q is equal to 3 is very easily it can be 3 or it can be multiple of 3, but in this case the 3 is only we are getting here 1. So, this option is better, and again this improvement of the transformer utilization as well we can improve upon, means this can be further improved by having the 3 phase configuration. We will see So, this option here is a better option compared to the option 1. No doubt here the DC voltage output is more than this value, but this is utilization is better here compared to this. You can argue that the difference between these is not very much, but here the difference is, I think it is a sometimes phi of something, but here this utilization is more important because the cost of the transformer is very expensive. We can go for some series addition of the valves, even though sometimes we put some extra valves, no doubt. We put several extra valves so that even the one valve get punctured, then we should not take it our converter circuit out from the HVDC link. So, it was believed that having this 3 is another advantage, that we are going to have the Q is equal to 3, due to that we are having 3 phases. So, it is very easily we can form the commutating groups, and we can very successfully we can operate the converter circuit. So, here as I said, whatever I said here, it is written your number 1 and your number 3 are the suitable, but the transformer utilization factor is better for 3. Since AC supply is 3 phase and commutation group are 3 valves, can easily arranged, is very easily arranged. Otherwise, you can say 2 in one group here and there, it is very complex system. Another the best advantage of having 3 is here. You can see the transformer utilization factor can be further improved by factor under root 2 while decreasing the number of winding by a factor 2. What its meaning? Means we are, suppose you are going to have the 6 winding transformer, in the same 3 winding transformer you can use for the return as well. Means one winding can be used, one is going, another can be used as a return at the same time. And thereby what happens, we can get our utilization factor will be improved by under root 2. Where it will be improved? It will be only improved here, this IT will be now is not like that. For you can see the for bridge circuit, this value your RMS value will be here your ID by what will be this value? Under root 2 by 3. Means here this RMS current is improved by under root 2 times. How? You can see here what happens if you are going for the bridge converters. Now, you can see the figure here. In this case, here your valve here 1 is conducting for 120 degree, and then it is coming here, maybe your 1 and 2 is conducting, here this is coming, and again you will find sometimes 1 is also conducting, means this phase current here will be 120 here conducting, then 60 off both sides, and then we are having here 120 for valve 1. So, your the current in the phase A will be here 120 it is conducting for valve 1, and here your valve 4 is conducting. Now, you can see that now RMS value here is now we are getting for this one. If your axis is this, then you have to add here another value, that is this is your twice pi by 3. This is 60 degree you are adding, how much this value? Pi, and this value is how much? This is you can add 5 pi by 6. So, here we are just again integrating to 5 pi by 6, 5 pi by 3, yeah, right. So, it will be here 3. Now, we are getting ID square d omega t. Simply what happens here, this value becomes twice, and then you are going to take here this your IT will be under root twice by 3 your ID. Now, you can see this RMS value here is improved by under root 2 times, means I can write here it is your under root 2 ID divided by under root 3, this was your Q is equal to 3. Now, you can say this is general. So, by using the arranging in a such a way here, and that is why this bridge rectifier, also known as the great circuit, is the best popular combination for the converter application, both rectifier as well as the inverter. So, here with this whole analysis, now we have also arrived this bridge converter is the best suitable for our HVDC application as well, because we are getting all our desired features for our converter configurations. Here this is the circuit here. Now, we have to analyze this circuit, and in this analysis it is assumed that here the inductance, this is having the winding inductance here, but this value is very insignificant. We are having the balanced 3 phases of the secondary side, and the numbers are made in a such a way that we will see the conduction pattern should be in the symmetrical order, so that there should no need to remember. So that is why here 1, 3, 5, 4, 6, 2 are denoted, and here it is assumed as a same, which I said the DC current is the constant in this link. Now, in this analysis we have to see, now one is the very important thing here, that we have to go for the phasor concept, should be very clear. Before that, here now again we will see the for 12 pulse converter same analysis can be repeated. Whatever the table which I have represented for the 6 pulse, you can again write for your 12 pulse, and you will find that here your Q is equal to 3 will be optimal, and just you have to find which value is the optimal for putting all this possible combination, because for your P is equal to 12 you have a lot of options. It is your Q, S and R. Now you are going to have here, let us suppose 12, 1, 1, then you are having 6 here, here 2 into 1, here 6, 1 into 2, then you are having 3, 1 into 4, and here 3, 4 is to 1. Then what else option we are having? 2, we are having 2 also, 2, 6, here 1, even though we can have the 2 here also, means we can go for this option here 3, 2 and 2. So you are having large options, and again from that table you can write the values and you can find that which one is going to be suitable options. So you have to choose the suitable options, and then you have to decide which one will be the better option. And this will be your assignment, one of the problem of your assignment, to calculate all these values and see which option, which alternatives or which combination is giving the best option. But if you find from here, and if you can use the same configuration here, if you see, if you are shifting by the 30-degree, because we are having the transformer connections star star and star delta, there is a 30-degree shift, and if you are adding the 2 6-pulse converters, you will find the best solution. So in this case what happens, you will find the Q is still 3, and then you will find there are 2, S is equal to 2 and R is equal to 2, and you will find some combination. Just you go and see what value you are going to get. Now to analyze this circuit, we have to see what are the conduction pattern of the valves, and you know there are the various type of conductions. One is the very ideal case, when the current from one valve is suddenly taken care by another valve of the same commutating group. Again the commutating group here, if you will see here the commutating group in our case, this is one commutating group, this is another commutating group. So for example, if your valve 1 and 2 are conducting and 3 is going to get the pulse after 60-degree, then the current from here 1 which was flowing here I1, that was the IDC, now it is going taken care by the valve 3, means suddenly it should be changed. So this is the ideal condition, but it will not happen due to the inductance of the winding. It is not so. So there will be some overlap degree overlap of from the current which is taking care from valve 1 to valve 3. So if at all the instant only one valve in a commutating group conducts, then it is called there is no overlap. Again the same concept here, that's here if valve 1 in this one is only one is conducting at a time, either upper and lower. So for example, your 1 is conducting and your 2 is conducting, then it is, and then after if you are firing 3, 1 is suddenly off and 2, 3 is are conducting, means it is there is no overlap. So it is the ideal case. First we will go for analyzing the ideal case, then we will see if 1 and 2 both are in the same commutating group, the 2 valves are conducting, and then what will be the output voltage, what will be the pulses, what will be the harmonics, what will be the current in each valve, and how they are going to share, we will analyze completely for this 6-pulse 3-phase bridge converter circuit. Now here let us see the conduction sequence. Conduction sequence, as I said, the name the numbers of the valves are given in such a way that you can very easily recognize. For example, as I said here, let us suppose 6 valve is conducting, then 1 is fired. So, 6 1 are conducting, then it will be your 1 2, then a 2 3, here 3 4 4 5 5 6, and then again we are getting 6 1, means this is again the repeated. So, all these pairs, they are conducting for 60 degree. So, this is a complete cycle. If we are starting from here, this will conduct for 60 degree, this will be for 60 degree, and so on and so forth. Here you will find it is 360 degree from 0 to this one. Now, if the two valves in a same are conducting, so that can be represented by the graphical way, and it is very easy to then recognize. You can see here, if I can draw the upper valves number here, upper valve is your 1 3, here 5, then again it will be 1. The lower valve here I can write here, lower valve here always it will be the mid of this. So, this is your 2, here 6, here your 4, here again 6, and again here we are getting the same 2 and etc. Now, you can see here the pattern which is conducting. Now, you can write here is easy to write, and then we will see, because why I am writing here at the later stage we will see what is the overlap angle when the 2 valves are conducting, when 6 valves 3 valves are conducting or 4 valves are conducting. This very easily can be calculated by this figure. So, in this case here you can see 1 and 6. So, I can write 6 1 are conducting. Here you can say in this period it is 1 and 2 are conducting, as the same sequence we are getting. Here it is your 2 3, here it is your 3 4, here your 4 5, here it is your 5 6, here again we are getting 6 1, means it is repeated. So, this is basically conducting for 60 degree, means all this here 60 60 60. Now, you can see 6 pulses. So, it is total 360 degree in one cycle. Now, if it is slightly, there is a current is not suddenly changed from 1 here, now I can change here, it is just means it is taking some time. So, simply here I draw the dotted line, or I can use the different color to clearly mark it. So, here I can say this is your this and here this. Similarly, here also we have to change it. Here I can say here, here and here and here. Now, here we were assuming that it was instantaneously changed, but now you can see it is taking some time, and this period here is known as overlap angle U. The U will be used for the overlap angle, means this is the period in the degree that the current from 1 is going to be shift to 3, means this period taking, means both 1 and 3 are conducting during this period, and this period is known as your overlap angle. Now, you can see now whole your pattern is now going to change, and now we are going to get, now in this case here you can see, if we are going to write at this point 1 6 and 2. So, here 6 1 and 2 are conducting during this period to know it, and this is your angle U, means your 6. Here you can just see here this if you are drawing the point here 1 2 and 6, means 6 1 and 2 are conducting at this period. Now, in this period you can see here up to here is 1 and 2 is only conducting. So, it is 1 and 2. Similarly, we can write here it is 1 2 and 3 and so on so forth. We can write again here it is 2 3, here 2 3 4 up to here U, here we are getting 3 and 4, here your 4 5 6 not 6, it is a 3, 4, 5. Here we are getting where? Why it is 3 here? Basically, it is not drawn properly here because this u will be small, here this will be this. But sequence pattern we are getting 6, 1, 2, then 1, 2, 6 will off because your 6 and 2 are in same commutating group. So, here this 6 will go away. So, 1, 2, 1, 3, 4 here, 1, 2, 3 here, then 2, 3 because 1 will off because 3 is taking care. Now, 2, 3, 4, now here 3, 4, now 3, 4, 5, now we will get 4, 5, now we will get 4, 5, 6, and then we will get your 5, 6, and then again 5, 6, 1, and so on so forth, because again we are coming back to this. So, now you can see at the certain point of time the 3 valves are conducting, and certain period it is your, this is the 2 valves are conducting. But the total duration here is your 60 degree. So, what happens, the remaining here, this is your 60 minus u degree when only the 2 valves are conducting. This is not always correct, because if your u degree is very large, means for example, let us suppose this is taking care a longer time, means this is going up to here. So, there are possibility, because the current from one changing from another here 1 to 3, it is taking longer degree, which depends upon so many factors, which depends upon your inductance, which depends upon your circuit condition, whether the weak AC system or the strong AC system, what is the DC value of the link, so many factors are involved. So, if it is taking more, now there is a possibility that you are getting the 4 valve conductions, and once it is getting 4 valve conduction, this is just like a short circuit, even though there is a possibility that this is taking the 60 degree u. So, we will get the different modes of operation, means if your u is 0, then it is always it is your 2 valves conductor. If u is 0, as say it is ideal case, it is your 2 valves are conducting at a time, one from one commutating group, another from another commutating group. If u is less than 60, if u is less than 60, here it is not coming up to this point, means we are getting the 2 or 3 valve conductions. 2 or 3 means sometimes 2, sometimes 3. Already this is the example when u is less than this. If your u is 60, then it will be 3 valves always. If your u is greater than 60, then you are going to have 3 or your 4 valves. And once you are coming here at the 4 valves, it means there is a dead short circuit in your converter circuit somewhere. So, always we try to operate our converter circuit that should be less than 60 degree u overlap angle. But there are some conditions, especially during the fault conditions or abnormal conditions, you have no control over u, and therefore, it can land up here in these cases, and that is very dangerous. So, we will analyze all these cases one by one, and we will see when it will be short circuit, what will be the harmonics that will be injected to the circuit. So, all these various modes, I can say the modes of operation. This is a mode 1, mode 2, mode 3, and so on and so forth, and we will analyze in detail. So, here now, as I said, to make analysis very clear and concise, now you can see now we are landing in the very complex scenario when the various valves are conducting, what will be the output voltage, what will be your valve voltage, what will be current, and for the different modes, we must be very careful about the phasor concepts, because this phase, if you are not missing here and there, then certainly this you cannot analyze the circuit, and you cannot get the complete output voltage of either valve or your DC circuit. Now, just I will go for some review on the 3-phase circuit voltages which will be used for this analysis. Now, you can see here I have taken, you will see here this slide, here EBA I have taken as a reference voltage. The reason is here EBA is the commutation voltage for valve 3. Now, in whole analysis what I will follow, I will take the valve 1 and 2 are conducting and 3 is going to be fired. For in this circuit, now you can see that what will be the commutation voltage, because that is the commutation voltage is also very important here for this valve. Let us suppose your valve 1 and 2 are conducting. What will be the voltage here when it will be going to be positive? If your 1 is conducting, then the voltage here at the cathode of this valve will be EA. Now, if your the 2 here is conducting, so what will be the voltage here? This is always EB at the positive. So, the voltage across this is EB minus EA, and this is the voltage. If it is a positive and you are giving a gate pulse, then only it will conduct. So, the commutation voltage is the voltage when your valve is going to conduct if there is a gate pulse, because if it is the EBA is negative, it will never conduct whatever the pulse you are going to give. So, the EBA is the commutation voltage of valve 3. Similarly, you can calculate the commutation voltage of other valve. Here I want to calculate what will be the commutation valve of 6. Means if you want to calculate the commutation voltage of this valve 6, you have to see before that 6 is going to come, what were the conducting pattern. It was your 4 and 5. Before the 6, 4 and 5 were conducting. Now you are giving the pulse to 6. Now 4 and 5 are conducting, means here your 4 is conducting, means here it is your EA. If this 4 is conducting, means this phase is coming here, this short circuit means conducting is the 0 resistance. Here at the positive is A, EA, and here it is always EB. So, it is EAB is the commutation voltage of this valve 6. So, similarly you can find out the commutation voltages for all the valves, means this is the voltage when it is being positive and the gate pulse is given, then this valve will conduct, otherwise it will not conduct. So, in my here the voltage representation, I am going to take as a reference here as EBA is as a reference. Here this line to line voltage of EBA is, we are going to take here as a reference the region here. Now, this is your, let us suppose here it is EBA, I am taking as a reference, means here this will be the instant when the valve 3 can be fired, because this is the commutation voltage, means you can fire at this instant, or even though after delay of any angle alpha, this valve can be fired, because before that 1 and 2 were conducting. So, 3 can only ignite from this position to up to this position. So, in our all analysis, I will assume that 1 and 2 are conducting and 3 is going to be fired. So, here as a I am telling here, I took this EBA as a reference, only the reason that the EBA is the commutation voltage of valve 3, and we will analyze all our circuit assuming the 1, 2 were conducting and 3 is going to be fired. Now, once EBA is given to you, then you have to write the other phase voltages and the line voltages as well. And if you know this and you can draw correctly, then you can have the complete wave shape across any valve as well as your DC output voltage. So, here you will see this is a 3-phase circuit. Here I can say this is your EA, here it is your EB, here it is your EC. Now, this voltage will be your EAB, because always we write here this voltage minus this voltage will be the arrow here is your EAB. Now, this value here I can write this will be your ECA, because EC minus this will be your this voltage, and here it is your EB minus C. This is, as you know, we have assumed the balanced 3-phase circuit and it is the positive sequence voltage. So, here your this sequence will be A, B and C, that is clockwise. Now, you can see here EAB is just like your x axis here, EAB, not EBA. But our reference which I have assumed here, it is your EBA, means here it is our reference. This is your EBA. Now, with this reference here, I want to write what will be the first the phase voltages. This is your A. To write here the expression for this EA, I want to write, first we can write here EBA, it is your under root 3 times EM sin omega t. Now, this A phase I want, the angle between these two will be the angle. Okay. So, now I can write here it will be your EM, because the phase voltage here it is line to line voltage under root 3 times. So, phase voltage will be EM. So, we can write here sin omega t. Now, we have to write the phase difference, whether a plus or minus. Now, what will be this angle? Here this angle will be is 60 degree. Are you sure? So, this is your 60 degree. What will be this angle? 120 means 2 pi by 3. No, this angle will be 30 degree. So, this will be your 30 degree. Just see it here. This degree is 60. This is half of this is a 30 degree. Here it will be 150 degree, means it is 5 pi over 6. So, this will be your 5 pi by 6. Basically, from this phasor, that is very important, that you should know which angle is how much. And you know, for writing this difference here, we have to take the tips of this. Either you for angle here, both vectors are going out, so this angle will be the phasor angle difference, the minimum angle. Or if the both are coming here, you can also take this angle, then that is also equal, because you know just extend it here, this angle will be the same. So, to calculate the angle, always it is not like that you are taking this and this angle here. So, this is wrong. So, that is why here I am telling this is very important to know the phasor concept here, so that you can write the various voltages. So, it can be asked to write your DC output voltage in terms of phasor value, in terms of your line values, or even the wall voltage in terms of all line or your phase voltage. So, this is very important to calculate it. Now, we have derived that this angle is 150 degree, that is the 5 pi upon 6. Now, whether it is a leading or lagging, whether it is a plus or minus. So, it will be, you just rotate here, it is just behind this. So, it will be plus. For example, in this sequence, this angle here, this is your V, this is I, this is the reference, this current here is a negative, because this is ahead. The current if it is this side, it is your positive. So, you just see it is rotating here, you are having the positive and this will be positive.
Sir, it is 120 degrees. Sir.
So, again we have to see whether it is a 120 degree or 5 by 6. Now, here again we can write, it is no problem. So, we derived here, we wrote this equation for the phase A voltage, that is Em sin omega t plus 150 degree, that is a 5 pi upon 6. Similarly, I want to write for EA. This will be again, it will be Em sin omega t. What will be the angle? Now, we are talking about this your EB, sorry, here, because already we have written here EB, and EB is this phase. So, this is the both tips are coming here. So, this angle will be 30 degree. So, what we can do now, we will see which one is a lagging, which one is leading. So, this angle is your 30 and 30 is nothing but your pi upon 6. So, it will be your pi upon 6. Now, whether it will be your positive or negative?
Yes.
It will be positive, because that's here you will see this is just behind this. Now, we can write your EC. EC will be your Em sin omega t. Now, we have to see plus or minus. Where is C? This is C. You see, So, this is here, means this angle is your pi by 2. And what will be this angle? You see, this is here, this is your, this C is your lagging, so it will be minus. To again, this is your EBA, this is your EC. So, just rotate here, you will find, means we can write this is your EBA and this will be your EC. So, this is lagging, and lagging means it is a minus degree. So, minus pi by 2. Similarly, we can write for this other line to line voltage, means I want EAC, I want EBC. So, no doubt this is the phase voltage is EM, this magnitude of the peak magnitude, this RMS is here, means RMS is your EM by under root 2. So, here it will be under root 3 times EM now sine omega t. Now, only we have to find what will be your plus or minus the phase angle. Similarly, I can write here under root 3 EM sine omega t, we have to find the plus minus what is the leading or lagging the angle. Now, from this figure again, now this figure becomes very dirty, but still we can find it. Now, I want to write EBC. EBC is your BC, as I said, it will be this your EBC. Now, this angle is 60 degree, means it is pi by 3. So, here it will be your pi by 3. Now, we have to see it is a plus or minus. So, this is your EBC, it is your plus because it is your leading. Similarly, we can write for this, that is your ECA, it is written here, means we are going to have EAC will be this one. Your EAC again I can write here, this is your EAC will be this arrow because this ECA is in this direction. So, this is both tip, here this angle will be 120 degree because this is your 60. So, it is your twice pi upon 3 and I can write twice pi upon 3, what will be angle? It will be again plus because it is rotating. So, these are the various voltages again which I have written the same here, and you know if you are going for change here from CA here, it will be simply the difference it. So, either you change here minus or you change here angle, you can add it, you will get the same. Or you can write from here again, that is why I am telling you this concept should be clear, then you can get each and every voltage very clearly. How these phasors, taking any reference, now I can change the reference, you can get the other values of that reference. So, these will be used when we will discuss about the complete analysis of the converter. Means we have to go for the various voltages, we have to draw on the even the sheet here, and then we will see the various voltage which is going to appear across the valve and what will be the DC output voltage at the same time. Now, to make the analysis of the converter circuit, again we have to go for the various assumptions. Here the assumptions even though up to 1 to 3 are the same. Here as I said the power sources are the sink, they are the balanced, consisting of the balanced sinusoidal EMF of the constant voltage and the frequency, and we are assuming that it is lossless. So, source it is giving imperfect voltage and current, having your the voltage is constant, frequency is constant, but the current can vary depending upon the conduction of valve. The second assumption is your the DC current is ripple free, means we are having the perfect DC current, and then here we are assuming the ideal valves, means valves are lossless and they are offering the 0 resistance in the conduction mode and offering the infinite resistance when it is in non-conducting or off state. Another fourth assumption here which are extra we are using compared to the previous assumptions we made when we are going for the rectifier circuit analysis. Here the ignition of the valves are equal intervals of the 60 degree. Means here we are giving the pulses to the valves at after every 60 degree. Means here your let us suppose here valve 1 2, 3, 4, 5, 6 and here it is 1 again. So, if we are giving here at the 0 instant here this valve is going to be given, you are taking this as a 0 axis, then this valve is going to get a pulse after 60 degree. Similarly, here now it is going to be 120 degree and so on and so forth. And it is equal intervals here we are giving the pulses. The region here we are assuming the symmetrical conduction pattern that is appearing across the converter circuit. There is a possible you can delay here it is 0, you can give this valve to after maybe after 60 degree. But we do not want, because if you are delaying here it will conduct, because if the commutation voltage across this is a positive, you are giving the pulse even though after certain degree it will conduct, but your output pattern will be not symmetrical and it will give lot of harmonics to your system. Current will be something different, so we never want it. We always operate in the very systematic manner. So, this assumption shows that we are giving the valve pulses to the valves after every 60 degree to the consecutive valves, so that we can have perfect ripples in the DC output and also our conduction pattern should be symmetrical. So, this fourth assumption is very important now, because we are going to analyze our converter circuit, and with this we will see the various voltages, various outputs, various currents, various frequencies. Here even the harmonics will analyze for the various modes of conduction. So, here in this lecture, today's lecture, I can see now what we did. We analyzed the configuration of our 6 pulse converter configurations for the various value of Q, R, S for P is equal to 6, and then we analyze this what will be the voltages. Those are taking EB as a reference, the various voltages we saw, which will be used in your next lecture. So, with this I just close this lecture, and the next here we are going to analyze the 6 pulse converter circuit without overlap angle, means U is equal to 0, and we are going to use all these sinusoidal voltages for getting the valve voltage, output voltage, and also we will find the current across the conductor valve. Okay, with this I can close this lecture. Thank you.